Oh, okay. Sorry. Okay. Can you hear me right now? Okay. Okay, perfect. So I was describing about the classification about manipulation and the difference between gross and fat manipulation is how we see this in my research group. So gross manipulation is the coordination of these large body parts and movements, and basically corresponds to the different behavior that we can have from extremities, from limbs. It's important here, as I was describing, that this type of activity that we can do with that with gross manipulation can be precise or can be rough. So, for instance, when we need to hammer, for example, in the picture here, uh, there is part of that activity that is very rough, is very large in the motion, but at the very end you need a very precise control to be able to hammer the what you want in the position that you like. So the second part is fine manipulation, and usually we associate this with hands, okay, with fingers. So basically the coordination of small body parts and movements. So this includes the motion of fingers, the motion of wrists, and of course in general of the hand. And there are multiple examples of this. So from playing piano to writing and other things. And here again, we can have precise motions or more rough motions. Okay, so in my research group, that is the REDS lab, is the Robotic Manipulation Engineering Design and Science Laboratory. We focus on the analysis, design, and implementation of robotic systems that can purposefully perform physical changes to the world around us. So we have uh, two broad research interests in gross manipulation, in robotic gross manipulation, and in robotic fine manipulation. So basically, we focus a lot in conceiving new types or manipulators and end effectors, new concepts and new technologies. And basically, we follow a theoretical and a practical approach. We are interested in investigating what can be built from the laws of mathematics and nature, and 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 to obtain manipulators and end effectors from these mathematical models, and that can improve the state of the art. But one very important part of our research is the practical aspect. So we build robots, we build things from scratch. We need to test the things because in manipulation, from my perspective, you can have multiple simulations and everything, but the real world is different, and we have to deal with that, and we have to develop robot hardware that is able to be reliable to the uncertainties of not just the environment, but also the uncertainties that come from the robot itself, from the sensor, from the actuators, and so on. So our long-term goal is to create robots from scratch that surpass the manipulation capabilities of certain humans and other animals and their diversity and uncertainty. We have multiple research areas right now, and in this talk, I'm going to focus mostly in four of these aspects that we are working right now. So I'm going to talk about quantum modeling and characterization, of course, about gesture manipulation, about in-hand manipulation, analysis, and planning, and about the design of mechanically intelligent robot manipulators and hands, and particularly now I'm going to focus on hands. Okay, I'm going to start talking about underactuated hands and basically how we can leverage this technology to improve the gesture manipulation of robotic hands in general. So underactuated hands and underactuated fingers can produce passively adaptive graphs with minimal control and hardware complexity. So this has been a very successful approach and has allowed us to develop to grasp objects with minimal control needs and very, very reliable. So there are multiple examples of those technologies. Here we see the video of one of these robot hands performing multiple grabs. But the thing is that dextro manipulation remains a very difficult task, not just for underactuated hands, that are the hands that, from my point of view, have mastered how to grasp objects, how to grasp irregular objects with a very simple approach. Of course, stand grasping to dextro manipulation for this hand is difficult, but it's also very difficult or even more complex for redundant actuated hands. So the question here is what we can do to improve these limitations. So to put the things in context, in-hand manipulation is basically the extension of the utility of hands beyond just acquiring and maintaining grasp. So we want to grasp an object, and from grasping that object, we want to modify the location of the object, okay, the position and the orientation of the object in order to perform another activity. Okay, so we are going beyond just grasping. So the solutions for enhancing in-hand manipulation capabilities can be broadly classified as extrinsic dexterity and intrinsic dexterity. So extrinsic dexterity corresponds to these approaches that use resources extrinsic to the hand, for example, a table or gravity, because gravity is something that is external to the hand, in order to improve or to facilitate the manipulation that you want to perform. Examples of this extrinsic dexterity approach include in-hand grasping and gauge manipulation, because you use gravity for improving that. So there are several researchers that have been made important advances in this area, and basically one of the important aspects here in extrinsic dexterity and in general the approach that we want to follow here is that we want to make things that are reliable in open loop first. So things that can control the object, manipulate the object in open loop, because our hypothesis is that if we develop the best open loop hardware that is very reliable, later when you close the loop with any type of technology that you want to follow, so classical control or machine learning approaches, your results should be better. So in extrinsic dexterity, we have seen some examples of multiple manipulations, like the flip, the pitch shuffling task of a coin, or for instance, the reorientation of cylinders, and so on. And here you see that you are using external features to the hand in order to accomplish these activities. In intrinsic dexterity, the manipulation of an object is achieved by applying forces to the object through the fingertips. Okay, so we grasp the object and we just rely on the forces that we can exert from the fingers in order to change the orientation of the object. So this is the typical definition of what we call dexter manipulation. So in this area, there have been three main approaches to improve or to enhance the hand manipulation capabilities of our hands. One is, of course, the use of high fidelity contact sensors to close the loop and try to manipulate the things easier. Another very successful approach has been the use of active or sliding surfaces on the fingertips. And another approach is that you grasp the object, you explore the word space of the object, and now that you know the word space of the object, of what is called the dexter word space, you can propose planning algorithms. So I want to focus a bit in the second aspect about active and sliding fingertips, because it has been successful. So basically it corresponds that you add some kind of actuator, and a slider actuator or a rotatory actuator in your fingertips, and you basically can, in that way, can control the object. Of course, the results are good, but we are more interested in understanding better how we can perform these activities directly from the forces of the fingertips. And one of the reasons is because one of the problems with active surfaces is that you, in the end, deal with the problem of controlling the cooperation between these new actuators. So you have the actuators of your hand plus the actuators of the fingertips, and the coordination of these things in order to perform the activity is not necessarily straightforward. So our approach is a new intrinsic dexterity approach that is based on the use of flexible and adaptive mechanical components that generate predictable behaviors of the hand object system. And this is our main difference and how we depart from previous approaches. So basically, we see the object and the hand as a whole system, and from there we evaluate how that system can behave and what we can do in order to obtain different motions that could be useful for the object. So the three aspects that we have focused or we have studied for reaching this or pursuing this approach have been contact modeling, manipulation analysis, and design of robot hands. I'm going to briefly talk about them and what we have done so far about that. So I'm going to start talking about contact modeling. So the type of contact interactions which can occur between a grass object and a fingertip are usually classified in 9 categories. So the first category is, of course, there's no contact. So the object has 6 degrees of freedom. And the other contact characterization that we have are point contact with friction, line contact without friction, point contact with friction, planar contact without friction, and so on. And here I indicating the number of degrees of freedom that we have with these typical with standard contacts or models of interaction between an object and a fingertip. So the classical or the more useful contact characterization or contact models that we have in robotic manipulation are point contact without friction, point contact with friction, and soft finger. And this is the case because basically these contacts are useful for arbitrary objects. It means that there is no an assumption of how is the geometry of the object. This is true for point contact with friction and soft finger, but it's not true for point contact without friction. But it is traditionally have been included in this set. But actually, the only 2 of those has indeed this characteristic. So with this, I would like to talk about kinematic equivalence of these contact models. Okay. A kinematic equivalent is simply a single kinematic constraint that represents the constraint motion between the 2 contacted bodies, between the fingertip of the object. That's a kinematic equivalent. It's a single kinematic constraint that describes these 2 things, and this interaction, sorry. So we have our 3 standard contact models, that is point contact with friction, and soft finger. So the kinematic equivalent of these contact models are, in the case of point contact without friction, is an spherical plus a planar joint. In the case of point contact with friction, is a spherical joint. And in the case of the soft finger, is a universal joint. And here we are just showing the different characterizations or kinematic equivalence of the standard contact models that we have. So a very interesting aspect is that this relation between the contact models and the kinematic equivalence is indeed the opposite. How in robotic manipulation we developed the concept of contact models was first that we thought, okay, historically how this was done was, let's model the connection between the fingertip and the object as a kinematic pair. That was the origin of the contact models. And after that assumption, we lead to the development of the contact models, and it was introduced by Salisbury in his PhD thesis, and it was also complemented by others later. So, as I was saying, all standard contact models using robotic manipulation are based on modeling the effects of a fingertip contacting a body as a kinematic pair. So when we realized about that, we started to think, okay, why if we can have a more general action of this interaction between the object and the fingertip, and we can probably have a more richer definition of contact models. So the natural generalization of the standard action of using kinematic pairs is to use kinematic change. So that was the natural generalization, and we started to explore that, and we started to explore how we can model the interaction between the fingertip and the object using kinematic change. So we have proposed this kinematic chain-based contact model. This contact model is based on what we call an extension of the Bruinig-Hund approach of surface-surface contact. Here, this represents the boundary of the fingertip, and this here represents the boundary of the object. And this model is made of serially connected revolute joints, where these two revolute joints of here corresponds to are located in the curvatures and the center of curvatures of the fingertip and the center of curvature of the object. And here we have a revolute joint across the point of contact. We are in this model. We model a friction using what we call resistant passive joints, and we are locating these resistant passive joints in the fingertip. A resistant passive joint is basically, usually passive joints are modeled in a way that they move as soon as you exert any torque on the joint. We model friction by saying that in the fingertip, these three joints are resistant passive joints. It means that they can resist motion till some threshold, and when that threshold is passed, so it breaks the contact, because basically the friction eliminates that. We have opted to call these resistant passive joints instead of friction passive joints, in order to avoid implications of the geometry of these joints, because and the nature of the phenomenon. So basically, we just say resistant passive joints are those that can resist motion till some point of the till some torque. So thanks to this generalization, we have proposed a general classification of contact types. And basically, we classify 4 big contact types of this. Here, just we have some particular cases, special cases, and important is that all standard categories using robotic manipulation, this is the Salisbury taxonomy, including line-line contact without friction that was introduced later by Hunt, that was in the mid-90s. Are obtained as special cases of this generalization. And moreover, we have proposed new contact models from this generalization that are useful. Here, I'm not going to go into detail, but we can prove, or we have shown that how the assumption of your contact model can lead to wrong results of your analysis. And for that reason, it's important to have a larger classification of contact in order to try to mimic better reality. So with this, I'm going to talk about manipulation analysis. So this has been our first approach, our first goal to enhance manipulation. So in manipulation analysis, we have focused in what is called, or what we call precision manipulation, okay? In precision manipulation, we define precision manipulation as when a grass object is repositioned within the hardware space without breaking or changing the assumed contact model, okay? So, and this is very important because any time that you analyze manipulation, you are assuming some kind of contact. Okay? And in precision manipulation, we say, okay, it happens when we can manipulate the object without breaking or changing the assumed contact. So example of this manipulation include writing, include opening a door with a key, include using a scissors. So there are multiple applications of this kind of manipulations. So imagine that we have this three-finger hand. This three-finger hand is a very popular layout. It's the same layout that we have in several commercial robot hands. Our goal with this analysis is to determine the feasible movements to reposition any grass object within the hardware space without breaking or changing content, of course. And most importantly, we want to define which of these possible displacement can actually be controlled by the hand actuators without depending on external factors to the hand, for example, gravity or other things. So we want to understand really what is the motion of the object that we can control with the hand actuators. We call this precision manipulation analysis, and we have developed this during the last several years. So one of the important things of precision manipulation analysis is that in general it's impossible to do with the standard techniques for grasping analysis that we have. It's very difficult. It's in general not possible. So for that reason, we started to explore how we can do that, how we can characterize the motion of the object first, and later how we can determine what actually are the displacement that we can control of this object with the actuators that we have. So our method is based on the kinematic analysis of the closed kinematic chains associated to the hand object system. So imagine that we have this two-finger hand with opposed revolute fingers, so two opposed thumbs, basically, a very simple hand. So the first step is we model the contact between the fingertips of the object using the kinematic equivalence that we have introduced previously with the contact modeling that we have introduced. So for example, we can use point contact without friction, or point contact with friction, or tubular contact, or whatever you consider, depending also on the design of your fingertips, or for instance. The second step is we translate the hand object system into a closed kinematic chain, and we determine its mobility. And the third here, so for example, in the case of these two finger, two revolute fingers hand, we model the contacts with contact with friction. So the associated hand object system in this case correspond to a closed kinematic chains that is a 6-bar linkage with two RRS serial limbs, revolute, and spherical limbs. And the resulting mobility in this case is 4. So once we have this model, we construct the corresponding graph of kinematic constraints here. So we see the example of this construction of this graph of the kinematic constraints. So basically, we are describing how the constraint between the object and the link, and between this object and the link, between this link and this link. So we describe that characterization of the kinematic constraints, and we reduce this graph using Herbig's group theoretic approach to obtain actually what are the feasible displacement that we can control of the object. So in this case, for this very simple and basic example, the characterization of the displacement of this object of here corresponds to a composition of planar motions and a rotation around the contact points. That is the characterization of the motion that are possible with this hand for any object. So after these 4 steps, we obtain a definition of the general displacement characteristics of any grass object relative to the palm. Finally, what we want to do is to determine which of these displacement can actually be controlled by the hand actuators. And to this end, what we do, we repeat the analysis, but we log the actuators that we have. So in this case, on the hand, we have 4 actuators in general. Okay, so each for each of the joints that corresponds to the joint of the fingers. So if we run this analysis with these log actuators, we obtain that for the case of this hand of here, this motion of here, the revolution are along the axis defined by the contact points. So this of here means that basically there's a rotation along this axis defined by the contact points cannot be controlled by the hand actuators and depends on external factors to the hand. This is actually very intuitive. We can see this very easily. The issue here is that first, with this method, we can actually compute this kind of thing for different types of layouts, even indeed for any type of layout. And most importantly, we can actually understand what are the motion that we cannot control. This has implication in design, of course, and also for the control of the hand. Finally, I want to finish describing some of the design of robot hands to improve the hand manipulation capability that we have right now, following these ideas that we have introduced. I'm going to present three types of hands. It's one of the spherical hands, the GR2 gripper, and the coalesced topology. So the spherical hands are a series of underactuated 3-finger hand topologies that we have that have 2 curved fingers and a normal thumb. Okay, and the main characteristic of this hand is that when you grasp the object, any object has always an instantaneous center of rotation that is fixed and is always at some point relative to the palm. So basically, the motion of the object is always spherical. We think that this can be useful for facilitating the planning of the motion of the object. So for that reason, we explore that. So here we have 3-finger hand. 2 of the fingers are curved, and we have a thumb. So in general, in the first iteration, that was this one up here, we have these two curved fingers and an additional thumb. And basically, using the technique that we have introduced, we prove that the spherical motion of the object, regardless the characteristic of the object, so regardless the characteristic of the object, always the gross motion of the object is spherical. Of course, the specific particularities of that motion depends on the characteristics of the hand and the object, but in general, always the motion will be spherical. And we explore different kinds of thumb design. So we explore a tooling with a static base that corresponds to this one up here. So it's a typical 2 revolute joints here. We introduce also a pivot here in the thumb in order to enlarge the workspace. And in this case, we have the pivot without the additional distal joint. So, for instance, in the case of the tool link, this one of here, corresponding on the tool link to revolute joint with pivot joint, the extra pivot joint is controlled passively. So we added these elastic elements there in order to have the control of that passive joint without actually controlling that. And we also explored, this is an example of the curved fingers that we propose and a comparison with the normal fingers. And we also propose multiple fingertip designs in order to improve the assumption, because in the assumption of this hand, we were assuming in the design of this hand, we were always assuming that the contact between the hand and the object was a point contact with friction. So as we know that the kinematic equivalent of point contact with friction is a spherical joint, what we try is to mimic as better as possible the behavior of the spherical joint. So to that end, we developed multiple fingertips with a magnetic sphere there, and we cast the urethane of the corresponding to the fingertip in order to have a better performance. So we test this hand with different objects and compare the things, the behavior of the hand, also showing that it keeps the grasping operation. So we are not removing the grasping operation from the hand. I'm going to check my time here. So here we see an example. This is okay. Okay. Here we see an example of the video that we prepared for that. Here we see the limited in-hand manipulation capabilities of underactuated hands. So they are very good to grasp, but the motion are very limited. Here it is very important to highlight that the workspace of precision manipulation is indeed very small, and we will see that. And it's very small because by assumption, we cannot break contact, okay? So this kind of motion are for the reason I call precision manipulation, are very useful for precise tasks. So you cannot expect to have a very large workspace. But that said, the workspace that we have with the classical standard hands is not very good. For that reason, we started to explore how we can do that. So here we see we first run several experiments to prove the spherical motion of the hand. So we do that basically attaching magnets to the object in order to explore the different to show how we was the workspace of the hand. Here we see the example of the hand with the standard fingers, and we did that with different objects. So here we will see how it is the behavior in the case of the spherical fingers of the curved fingers, and in this case there is no a pivot at the thumb, so the workspace is limited. Here we see the final solution that I think was the best, was to add this pivot there with this elastic element, basically in a way that when the forces are exerted to the object, the thumb can respond to that forces by lending towards the size that is required, and of course you have a larger workspace. Of course, we will see that one thing is that if theory and reality is a different thing, because when you manipulate an object, you don't have these fixed constraints. But even that, we were able to obtain a better workspace. Here we see the fingertips, how were designed basically. So we see the magnets, and basically this icosahedron here was proposed in a way that it like cage the object. And we also propose other types of fingertips. So I'm going to advance. We are almost done with this video, so let's try to finish this. Yeah, here basically this is an example. So of the if you remember the first video of the underactuated hand, this is small, but the one was even smaller. Okay, so the change, as this is very small, any change here have a big impact in percentage. So that's important aspect. So the second hand I want to discuss today is the GR2 gripper. The GR2 gripper is an underactuated hand for open loop in-hand planar manipulation. So it is called the GR2 gripper because it means the grasp reposition reorient gripper. It corresponds to a two-finger gripper topology that enables and enhances predefined in-hand manipulation primitive. This in-hand manipulation primitive is the reorientation of the object. Basically, that is the planar reorientation of the object, and this enhancement is achieved or is possible for any kind of object. Okay, so why we wanted this? Why we wanted this to do this? Because single degrees of freedom two-finger robot grippers are the most common gripper in industry and in research settings. And this is the reason, because it's mechanical simple, is reliable, is low cost, have very, very good force capabilities. However, they can be limited, very limited, outside of pick and place operations. A typical example of this limitation is the alignment of parts before assembly processes. So for example, the pegging in hole alignment task. Okay, that is the type of limitation that you have with these kind of grippers, and you have to rely on the dexterity of your arm rather than the dexterity of your hand in order to perform this activity. This is a generic instance of a traditional two-finger robot gripper with 4-bar linkage fingers. This robot gripper is the most popular one. Here we have some examples, some images that I taken from Google. And the most important thing here is that this gripper, this mechanism, has been historically employed solely for grasping operation, without considering any feasible capacity of dexterity. So just to grasp, nothing else. For that reason, we started to talk about that, how we can maintain the simplicity of this gripper just to grasp, but let's add some kind of dexterity to this gripper in order to do something else beyond grasping operation. And for that reason, we propose what is called the GR2 gripper. Then the GR2 gripper, we also have this pivot in the palm that have these elastic elements, and we have a reconfigurable palm that allow us to improve the workspace. So one of the differences of the GR2 gripper is that previously proposed designs independently incorporate elastic elements in each finger. In the GR2 gripper, these elastic elements are coupled between these fingers in order to change the behavior of the palm. I'm checking the time because I have to go. Yeah. So as I was mentioning, I'm going through a bit quicker. So basically, in the GR2 gripper, when the GR2 gripper is going to grasp an object, it behaves as a traditional gripper. It behaves as a traditional gripper, just as a normal gripper that you close the fingers. And when you grasp the object, we have shown that when you grasp the object, you always can detect a thrust inside this object in that system. And for that reason, regardless of the condition of the elastic elements, that your grasp is guaranteed, geometrically speaking. So when we have dexterous manipulation, and how we propose the dexterous manipulation in this case is we propose a hybrid control approach where we have a pushing finger and an opposing finger. And the pushing finger is controlled using position control, and the opposing finger is controlled using torque control. Basically, during these in-hand manipulation tasks, the palm behaves as a reconfigurable linkage. So we have some examples of this is the traditional gripper, and the traditional gripper, we show that the traditional gripper can have some kind of dexterous manipulation. So basically, we're having a pushing finger and an opposing finger, just that. But here we show that by adding these elastic elements, we can have we can improve that behavior. This is basically the behavior of the GR2 gripper. Here we have the third example, for instance, with this circle, where we show the behavior of the traditional hand that have been classically used just for grasping operations, and here we see the behavior of the GR2 gripper. All of this is open loop, is controlling open loop, is just the result of the improvement of the mechanical aspect of the hand. Okay, so we have recently used this hand for model free hand manipulation, and this is one of the important aspects of this kind of research, because as we know that we can obtain a better range of orientation with the GR2 gripper using a very simple low-level control scheme that is pushing and opposing. I'm pushing in position of control and opposing with torque control. We have developed, along with some collaborators, the control of this behavior using tactile fingers, tactile sensors. Finally, I would like to talk about the coalesced topology. The coalesced topology is a result of an optimization of the year-2 gripper. So we started to explore how we can improve this range of orientation of the year-2 gripper. And finally, we obtained this new topology. This new topology is basically a result of a cascade optimization approach, where we were able to show that if we eliminate the palm, in this case, and we have a single joint there, so basically we are obtaining a new topology, because in terms of the topology of the resulting hand is different, we can get up to 90 degrees of reorientation and without any kind of control. We are just using here open loop control. So basically that. Yeah, with this, I think I would like to finish. So thank you very much for your attention. And please feel free to contact me if I can be of any help. And thank you again, Payo, for this invitation. Okay, thank you. Goodbye.